Now at this point of time, let's actually move on to some models for this H. Okay, now if you're thinking how big will H be, see typically, right, I've taken this H to be of the same size as F, right, in this case just 2 cross 2 or something. But ideally what will happen is this H will be a very small, which will have a support that's very small, that means it will be non-zero only over a few elements. Like seldom, right, will this H go beyond 7 cross 7 and all, whereas the image will be like 512 cross 512. So this matrix will typically be lots of zeros. Okay, it's not usually like this. You'll have lots of zeros in it, and there are various algorithms that actually exploit the sparsity of that matrix and so on. But then the circle and everything will still remain, except that H is typically H will typically have a very small support. And where this H comes from and how do we typically model is what we will talk about next. What is called blur models. Okay, blur models. And it turns out that only for optical blur you can have these models. The motion blur, which is the other kind of blur, you can't have these kind of models and all for that. Okay, so this is again only for the optical case. Okay, just to make it clear, we can't take this and use it for motion blur and all. Okay, so the blur model, see and we also call this H, right, is referred to as either a PSF or we call it a blur kernel. Kernel is just a commonly used term for a blurring function or a blurring operator. So you can think of it, see a discrete case, right? This will be a discrete set of values. This will be a 2D array with some discrete set of values sitting inside it, with some values sitting inside it, except that on the spatial grid it is actually a discrete kernel. Now, so this size is typically, right, max of, so you won't see more than 11 cross 11 and all, very rarely. Okay, not that it can't happen, but typically we don't go, I mean any image, right, if we take and blur it with a kernel, like, and the idea is that we don't go around blurring and all. It is simply to understand that is what happens inside the lens. So okay, it's not like we are interested in taking a good image and spoiling it. That is not the way. That's not what I mean. What I mean is when you see a blurred picture, you should realize that there is some PSF like this that is acting on the original pinhole image that you should have ideally seen in order to be able to give this kind of a blurry picture. And that blurriness itself, if you see, even with a 3 cross 3 or a 5 cross 5, you can see so much of blur that you don't need something very big and all for H. And generally it is not. Now the first model, okay, that is commonly used is what is called a pillbox model. A pillbox model. It's similar to a cylindrical, a pillbox, right? A pillbox is what, where you gonna keep the pills, right, at home. That's a pillbox, right? So it's like a cylindrical thing. So the pillbox model, it goes by ray geometry, purely by ray geometry. It goes purely by ray geometry, and according to which, right, under the blur kernel, I'm just writing a continuous case here. We'll talk about how we normally do a discretization. Okay, so a continuous case is easy to explain. So it goes like 1 by pi rb square, as long as x square plus y square lies within rb square and 0 otherwise. So what this means is that, and again, right, as you can clearly see, okay, one of the things that any kernel should satisfy, blur kernel, any blur kernel should satisfy the fact that hxy should be greater than or equal to 0, and then double integral hxy dx dy should be equal to 1, right? This is something that we said already. Okay, so any PSF for that matter should satisfy this condition, okay, if it's a point spread function. And as you can clearly see, right, this 1 by rb square, if you integrate it, that's the area, right, under the, so it'll automatically integrate to 1. Outside of it, it is all 0. So it's like saying that, inside this circle, okay, so you've got like I say intensities, and outside it's all 0. But normally what we do is, we like to deal with kernels that are regular in shape and not like circular and all. So what we will normally do is we'll kind of take, we'll inscribe it within a square, right, and then outside the circle we'll say that this is all 0, and then use that as the kernel. Okay, that is what is more common. Huh? Why does greater than or equal to 0? Because I mean you can't really reduce it. I mean you can't make an intensity negative, no? Through, I mean when a lens acts, a lens cannot make the intensity negative. I mean, it can only spread, no. It's like saying that, if you give an intensity, I mean, and if you see a blur, if there is no blur, you just see the intensity that you would have seen as a pinhole. Else, it has to spread, right? If you have a negative weight, I mean, when a lens is not supposed to take away things from the energy. I mean, it won't take anything, it won't add anything, but whatever is there should come up on the image plane. So the integral should sum up to the original intensity. So if you think of that as a blurring operation, then the blur kernel should be such that it sums to 1 and then all its weights are basically greater than or equal to 0. And okay, so one of the things is this, and so the thing is that, so it's almost like saying that, outside this blur radius, this RB is the same blur radius that we talked about, right? So this RB is actually the blur radius that, I don't know what was that equation, R naught, what was it, did we use U naught or V naught? I think we used U naught maybe. So R naught, U naught into 1 by omega d minus 1 by d, right? This was the expression, no, that we had actually derived for a lens. So this RB is the same kind of a blur circle, and right, in order to express everything in terms of the pixels, right, to go to the pixels, because we don't talk about blur radius in terms of centimeters and all. Okay, what is normally done is you multiply RB by rho. Okay, rho times, okay, one does rho times RB, where rho is a calibration constant, which is, which sort of tells you calibration constant whose unit is like number of pixels for that sensor. Okay, this is for that particular lens, for that particular image plane that you have per centimeter, right? So if you have an RB, let's say you have a sensor resolution such that you've packed like 5 pixels per centimeter, and if you have a radius that is like 2 centimeters, then it will mean that you have a blur kernel which is extending to a 10 pixel size, right? Because I mean, eventually, right, you have to have everything on a sort of a discrete grid. So this rho is something that, let's say, one has to calibrate a priori, and then one can continue to use it. But this model, right, just assumes that the rays will all, it's strictly limited to a circle outside of it, right? Everything will just fall off to 0 immediately after that, and so on. So more realistic model is actually a Gaussian model, okay, which I will write next. So more realistic thing is actually a Gaussian. Okay, so that was pillbox. The second is actually a Gaussian blur model. This is what is more common, but in MATLAB, if you see, right, they'll allow both, they'll accommodate both. Okay, but a Gaussian is more common. So there, I mean, so here it means that all the intensities within the circle are all uniform, they're all equal, right? So everywhere it's like 1 by pi RB square, and outside it just truncates off immediately to 0. The Gaussian blur model, right, makes use of the fact that this is a more kind of a realistic model, in the sense that what it says is, it takes into account various, say, effects. So one is what is called a diffraction effect. So every system is actually a diffraction limited. Okay, diffraction effects. What that actually means is that as you kind of keep reducing the aperture size, right, you may think that you will end up with a more and more sharp image, but then beyond a point when the aperture begins to become smaller than a point, then the rays actually begin to diverge. Okay, that is actually a diffraction effect, and these are actually real effects, right? So it basically means that so if I have to write it correctly, as aperture becomes small, rays begin to diverge than converge. Okay, which actually means that this assumption that everything will simply be 0 outside the radius of RB and all may not actually be true, because there'll be something that is actually going away. Diffraction effect is one. Then there is something called spherical aberration of the lens. Spherical aberration. What that means is refraction at the boundaries of a lens. Refraction at the edges or boundaries. At the boundary of a lens is more than at the center. And the other thing is all these are actually independent effects. Okay, diffraction is independent of whatever happens, and then there is something called a chromatic aberration. They called a chromatic aberration, according to which not all wavelengths will converge. Not all wavelengths converge at the same point. Okay, this may not be directly, you may not be able to see it directly, right? Visualize it, but not all wavelengths converge exactly at the same point. So there could be a small, we are assuming that, right, all of them will converge and will get exactly a point and so on. So there could be some spreading around that is going on, and there are also the other effects. Okay, so the main effects are these, and these are all independent effects. These are all independent sources of error in the sense. These are all independent sources of error to the actual model that you have in mind. All independent sources of error, and in the light of the central limit theorem, and there is also coma effect and all that. There are a bunch of other, and in the light of the central limit theorem, the net effect, right, of all these independent sources of errors can be modeled as a Gaussian. In the light of the central limit theorem, which you know, the net effect can be modeled as Gaussian. Okay, this is what. So, which is why in MATLAB and all, right, you will find that a Gaussian, it is what, let's say people, when they want to synthesize some blur and all, they will go use a Gaussian. If you are wondering why they use a Gaussian, this is the reason. And which then means that, so you are sort of saying that h of xy is some 1 by, 2 pi sigma square e raised to minus of x square plus y square by 2 sigma square. Again, right, so 1 by 2 pi sigma, so that it sums to 1, integrates to 1. And this sigma, right, what is the sigma now? Now, where the sigma is given as rho times RB, where rho still has the same meaning. And so sigma is now in pixels. So if you say that I have sigma equal to 1 pixel or something, now the point is, right, so what this is actually saying is that the intensity will kind of fall off, and it will also not something that will simply limit itself to only RB radius. If you look at that ray geometry model, it seemed to say that outside of RB, right, you will see nothing. But in reality, right, what this model is saying is that it will kind of die down slowly. It won't just abruptly end like that. And then the other thing, right, that it is also saying is that the intensity, right, or the weight for the kernel will be maximum at the origin, and then about that it will spread, and then the intensity will also fall off. Okay, and this so right, you might actually think that then maybe this h of x will then is going to be so big then, right? But we all know that if you have a Gaussian, right? So suppose I take a 1D Gaussian, okay, then we know that most of the area, right, almost 99% of the area under a Gaussian is covered within 3 sigma, right, on either side. So if you go like 3 sigma, if it has a standard deviation of sigma, and if you go plus minus 3 sigma on either side, we know that we would have almost covered, kind of say, 99% of the area under a Gaussian. So what we normally do is so when we do a discrete approximation, right, so because finally, right, what you need to suppose you had to implement something like this, right, you will need to do a discrete approximation. So discrete approximation. So in a discrete approximation, we take the kernel size, or we take the blur kernel size to be limited to ceil of 6 sigma plus 1, because there is also the origin, no, wherever the mean, right, about the mean. So 3 sigma plus 1. So ceil of 6 sigma plus 1. So for example, if I say that sigma is 0.1, then you will say like ceil of, what is it, 0.6 plus 1, so 1.6. So we'll say it's actually 2 pixels, right? But then one likes to have an odd sized window, because if it's even, then where is the center and so on, right? So we normally limit to ceil sigma plus 1, but then odd size. Okay, so what this actually means is that even if I get 2, I will still take a kernel that is going from -1 to 1, so that I get actually a 3 cross 3. and then because then it's clear to me as to what is the center. Even size nobody will take because that will create unnecessary problems, right? So you take an odd size kernel every time. So if you're not hitting an odd number, make it odd, make it the next immediate odd number, and then in this case it will be 3 cross 3. The only thing that happens is when you do a discrete approximation, right? You will do, let's say, HFM. One way to do it, the simplest way is 1 by 2 pi sigma square e raised to minus of n square plus n square by 2 sigma square, and you should remember that the center is here. So m equal to 0, n equal to 0 is here. So when you say 3 cross 3, you're going like minus 1 to 1 with 0 comma 0 at the center. So it's like I have a blur kernel. So in the center where my central ray comes, I'll have the maximum weight, and then around it will start to die off, right? So what will happen is if you just compute these values and if you put them here, they will not sum up to 1 because now it is actually a discretization. So what is normally done is you compute for a sigma, you compute HMN, you fill all those values here, then you simply compute the sum of, say, HMN calculated like this. Okay, sum up all of them, it need not sum to 1, and then you scale HMN by sum, right, each of the HMN. So now that you know that it will all sum up to 1, because you have to make sure that it is a blur kernel, right? It should not have something that is greater than 1 or less than 1 or something. Okay, so a simple implementation is where this m and n will go from, depending upon, suppose let's say if your sigma is 1.2 or something, right, then you will get like ceil of what is it? So 6 sigma 7.2 plus 1, right? So it's 8.2. Okay, so you'll take 9. So 9 is your total size. So your m and n will go from minus 4, right? So m comma n will go from minus 4 to 4, and then for those values we'll compute HMN. Okay, plug it all in here, and then take the sum of these values over this minus over this 9 cross 9 window. Okay, so it will be like a kernel, you know. So this kernel will be like 9 cross 9. Okay, 9 rows, 9 columns. Everywhere you will have a weight. Add all of them up, you will get a sum. Divide every weight by that sum. So now you have a kernel that is an approximation of this Gaussian. Okay, now at this point of time, right, what happens is actually you people will have a lab for this, okay, which is only to get you to familiarize yourself with how do you synthesize this kind of a blur. But in real life, we may not want to do it at all. Okay, this is only to understand the image formation process in a lens. So by implementing it, right, you will realize that that's how the image is getting formed. Not that we want a code that we will use to blur an image and so on. Sometimes, of course, people use it, right? If they want to mask somebody's face and they don't want somebody's identity to come up, to show up, right? That they do this, okay? But that's not our goal, okay? This is only to understand the image formation process. So the first part of that, so this is like lab 3, okay? And after this, I'll give a pause, okay? Because after this, I want to introduce some mini projects for you, and we will shave off a few of those assignments that we normally give and leave them as optional, okay? Now this lab 3, right? So the way this works is, so first is a space invariant blur, okay? So we'll give you an image, let's say it's some Lena or something, and now it is, because it is all synthetic, right? There is nothing like a 3D Lena phase. Will this introduce this blur and so on? We're just taking some image and then we'll just kind of say blur it. Okay, we are not. It's not like it is not really reflective of what will happen when if you were to actually take a lens and write image Lena. Right? Lena's face is it has some features, and therefore there may be space variant blurring and so on. But this is only synthesis in the lab. You can take any image that you want. We don't care about what its 3D structure is. Just take that image, and suppose I want to apply a uniform blur on it, I'll just apply it, right, and just see it. Okay, this is only for that purpose. Okay, so we can't start interpreting that if Lena had to be in front of a lens, then this is how it would have come. No. So this is only right for you to just play around with. So you take a Lena image, whatever image, I don't know what we give. So Lena, and then right, we'll ask you to blur it with sigma equal to 0.1. And if sigma is such that, right, your size is only 1, in the sense that, right, if I give you sigma to 0.01, then 6 sigma plus 1, right, all of that will simply end up with just 1. So that means it's like an impulse, right? So the blur is so small that there's actually you don't see any blur at all. So the minimum size will be kind of 1. The maximum can go depending upon whatever sigma you give. So I think we start with even something like no blur, which will be like 0.01 or something, I think. And then we'll give like 1, 0.5, 1, 1.5 and stop somewhere there, because at that point of itself you will realize that this image has become very, very blurred. And the way you will implement the convolution is exactly the same way that you would do in 1D. So here is your Lena's image, right, and there are all intensities sitting in each of these boxes, and you will take and given the sigma, you will have the kernel. You'll actually build the kernel. Assume that it is 3 cross 3. Then what will happen? So you kind of place that 3 cross 3 kernel here, right? So here will be the center. Here is where you want to know what should be the value of G now. So you would do the simple. So now you can flip the kernel, but this is all isotropic. No, it's Gaussian. Whether you flip or not doesn't matter. So if you want, you flip. If you want a proper code, flip it both along x and y. And then what will you do? You'll overlap it with the image under it. And then the image has some values here under. Your H has some values in it. Multiply, right, both, and then add all of them, and then copy them into G. Okay, don't copy it back here, right? You should not copy it back here. You should have a G. So this is your F, and then F is the black one, H is the orange, whatever, the brown one, and then, right, you will simply copy these intensities. Now if you're wondering what do I do at the boundary and so on, so this value that you get after convolution, copy it here, then slide to the next location, do the same thing, find out the convolution. That's how you'll get a picture that will look blurred now, right? Fairly straightforward. This is straightforward. Now, yeah, right, I just wanted to tell you that at the boundary, right, because what will happen, you also have to find the value here, no? Correct. So you're sitting here. Okay, you have your 3 cross kernel here, you want to say what value should I copy here. So only thing is, here the problem is that outside you don't have any values at all. So, but then in order to make sure that you don't end up reducing the intensity just because there's nothing outside, what we normally do is we ask you to just look at only at the boundary, take these 4 values under the kernel if it's 3 cross 3, and then scale them by their sum so that they sum to 1, and then simply take these intensities alone and copy that here. Just take a weighted average like that. Okay. Or you can make an approximation that this image itself repeats left to right. So this column, right, you can kind of think of it as folding around. I mean, you can do whatever approximation you want, or we don't really care. Even if you just copy this intensity there and put it, we don't care, because this is only at the boundary. So people make different approximations. You can make whatever approximation you want at the boundary. Okay.